Look, today we're stepping right onto the shop floor, and I'm talking directly to you as a junior technician who's really ready to level up. We are going to master the crucial, entirely invisible physics of solenoid lag. Honestly, this is the exact difference between being just a parts changer and a true master diagnostician. So if you've ever been burned by a phantom drivability issue that just made no sense, well, this masterclass is for you. Let's get right into it.
Okay, quick look at our agenda for today. We'll be covering the invisible solenoid lag, physics of the pull-in, injectors versus transmission timing, reading the back EMF notch, fluids, friction, and failures, and finally we'll wrap up with the Master Tech diagnostic tree.
Starting right off with Section 1, the invisible solenoid lag. So we're looking at those phantom faults that drive literally every technician completely crazy on the shop floor. You know the ones, the kinds of problems that make you want to just throw your tools across the room. I want to ask you a serious question. Why did your OBD2 scanner just lie to you? Picture this. You've got a car running terribly, zero codes. So you go ahead and load up the parts cannon and fire away. But the problem is still there. Why does that happen? Well, here is the brutal truth. A basic scan tool only sees electrical continuity. It completely misses the actual physical mechanical delay of a sticking solenoid. And it's exactly these delays that cause those real-world drivability issues. We're talking hesitation during acceleration, harsh thudding gear changes, a really lean idle, elevated positive long-term fuel trim, and misfires when under low pulse width conditions. Your scanner totally misses these because, hey, the electrical circuit is technically whole, but the mechanical actuation has a latency that you have to diagnose yourself. Moving on to Section 2, physics of the pull-in. Now we need to understand the root cause of our problem, and this right here brilliantly illustrates it. This is Faraday's law of induction in action, the time constant equation. Tau equals inductance divided by resistance. Basically, when you send voltage to a solenoid coil, the magnetic field doesn't just magically snap on instantly. It builds up gradually. It actually takes time for the current to reach roughly 63.2% of its maximum value. What this means for you as a tech is that absolutely every single solenoid out there has a physically unavoidable electrical delay built right into it. And you really have to look at how these two variables fight each other. Inductance inherently slows down the current rise time. It kind of drags out that magnetic force buildup. But then, look at the resistance side of our equation. Copper wire is incredibly sensitive to heat. As underhood temperatures rise from, say, 20 degrees Celsius up to 120 degrees Celsius, coil resistance increases by roughly 39%. That constantly changes your baseline resistance, so the actual physics of the coil are changing just from the engine warming up. Notice the huge difference here between drivers. Compared to a standard pulse control, modern engineers use a peak and hold driver to actively fight that time constant we just talked about. It slams the coil with a massive initial spike of around 4 to 8 amps to force a really rapid mechanical pull-in, and then it immediately drops the current to about 1 amp just to hold it there. This gives us that lightning-fast actuation without literally melting the copper coil in the process.
Okay, Section 3, injectors versus transmission timing.
Let's contrast the microscopic, rapid-fire world of fuel delivery against the heavy, fluid-pushing world of transmissions. On one side, gasoline direct injection fuel injectors require sub-millisecond precision. If they deviate by just 0.3 milliseconds, boom, you get a drivability fault. On the flip side, automatic transmission shift solenoids are moving heavy fluid. They operate much slower, in the 20 to 60 millisecond range, and have a somewhat wider 3 to 5 millisecond tolerance. But in both worlds, timing is absolutely everything. So the crucial takeaway here is this. Your engine control module and transmission control module are fully aware of this physical lag. They are constantly tweaking and adjusting firing times, using voltage compensation tables and adaptive pressure algorithms just to mask these solenoid delays. They're basically covering up the mechanical wear, until that wear finally exceeds their adaptation limits. Once the computer runs out of tricks, the customer feels that harsh shift or misfire, and the car ends up right in your bay.
Section 4. Reading the back EMF notch.
Now, put away the scan tool for a second. When you hook up a current clamp to a lab scope, you're looking at time domain analysis, which is like the hidden language of the circuit. There are 3 phases you need to master. Pull-in time starts from the ECU command right to the exact moment of mechanical displacement. Settle time is the period until the plunger is fully seated. And release time is when the plunger returns after the command ends. I really want you to laser focus on the pull-in time, because this is exactly where we catch our mechanical faults hiding inside an electrical signal. So, what are we looking for? The back EMF notch. This is that characteristic knee or tiny little dip you'll spot on your current ramp waveform. It brilliantly illustrates the exact microsecond the metal plunger physically moves inside the coil. As it moves, it actually changes the coil's inductance, creating a momentary magnetic disturbance, a back electromotive force that we can literally see on the oscilloscope screen. It's awesome. As a master tech, here's exactly how you read the matrix. If you look at the waveform and that notch is completely missing, the plunger is entirely seized. It never even moved. If the notch happens at an abnormally high current level, the plunger is binding up or facing excessive mechanical resistance. And if the timing of the notch is shifted compared to OEM spec, you got a sticking solenoid. See, the electrical circuit is technically intact, which is why your code reader passed it, but your scope just proved the mechanical part is failing.
Section 5. Fluids, friction, and failures. I want to let this number just sink in for a second. 20. At negative 20 degrees Celsius, automatic transmission fluid can be up to 20 times thicker than it is at normal operating temperature. That creates absolutely massive hydraulic back pressure. Your port transmission solenoid has to fight through a fluid that is essentially turned into syrup, which directly adds a massive amount to the actuation delay. And hey, it's not just the cold you have to worry about. During your physical inspections, you really need to look for real-world indicators of friction. Think swollen rubber seals from someone mistakenly using the wrong fluid chemistry that can drag on a plunger immensely. Look for carbon coking deposits inside fuel injectors, metallic debris and sludge in the transmission pan, and fretting corrosion right at the electrical terminals. Fluid condition and physical contaminants are basically the primary culprits for delayed actuation. Finally, Section 6, Master Tech Diagnostic Tree. Let's build your ironclad methodology. Here's where a lot of guys get it wrong, so memorize the sequence. You always start with electrical fundamentals before you ever touch the mechanical parts. Step 1, verify your supply voltage under a load. Step 2, measure your ground path resistance. Step 3, perform your current waveform analysis on an oscilloscope to hunt down that back EMF notch. And Step 4, inspect the mechanical condition and fluid quality. Notice the golden rule here: you do not touch a wrench to replace a single part until Step 4, period. I really want you to burn this quote into your memory. A high-resistance ground can mimic a mechanically degraded solenoid completely. Guys, this is the ultimate master tech golden rule. A corroded ground increases your time constant, creating a delay that looks exactly like a sticking plunger. The single most common rookie mistake out there is firing the parts cannon, replacing a perfectly good solenoid, only to realize the real issue was a rusty ground bolt the entire time. Seriously, check your grounds before you replace the part.
And as you're advising your customers, remember to highlight these preventative steps: maintaining proper overall system battery voltage, using the exact OEM fluid type and viscosity, sticking strictly to manufacturer fluid service intervals, and visually inspecting and cleaning grounding points. These aren't just shop upsells. These are the scientifically proven ways to prevent excessive solenoid response delay from wrecking a vehicle over its lifespan.
So here is my final challenge to you. After seeing how induction, resistance, and fluid dynamics control literally every single movement under the hood, are you still just going to be a parts changer reading basic codes? Or are you ready to actually diagnose the invisible physics of the engine? Grab your oscilloscope, remember to check those grounds first, and I'll see you on your next tough diagnostic ticket.